Okay, 1 through 6 are solved graphically. I should say 1 through 4 are solved graphically. Remember, when we want to solve any equation with real solutions graphically, we graph one side of the equation and then the other side separately, and we find the x value of the point of intersection. That will help with 1 through 4. Okay, in this video we'll be looking at problems from 16.3, Solving Logarithmic Equations. Remember our generic two-step process for solving special equations. Put this somewhere solid in your notebook, maybe the very back page. Solve special equations. What I mean by special equations are square root or square or absolute value or log functions. All these different kind of functions that we've been exposed to this year. And so we have this two-step process. The first thing we've done is we've isolated the function. That is the logarithm or the square root or whatever that is, whatever the special function is. Let's get it by itself. Isolate the function. And then our step 2 is to undo the function. Typically we're using the inverse. Undo the function. Think inverse. That's a V. All right. So number 1 here, we have log base 7 of the quantity 4x plus 1 equals 2. I'm going to write that a little bit larger so we can see it. Log base 7 of the quantity 4x plus 1 equals 2. All right, so let's remember our log rules. The product, quotient, and power rule, we've talked about that a whole lot. But the key is this definition. Remember, a log is an exponent. What I mean by that is the log function, the output is an exponent. A log is equals an exponent. The output over here is the exponent. We can convert from a log equation to an exponential equation using this definition. Log base b of a equals x can be converted to whatever the base of our log, that is the base of the exponential. The equals to is the exponent. A log is an exponent. And whatever we're evaluating the log of, that'll go on the right-hand side. B to the x equals a. B to the x equals a. B to the x equals a. All right, so the first thing we do is we isolate our function. Well, that's done here. We've got our function isolated. Our log is by itself. If we had something multiplied or something added or subtracted, we would want to get rid of that, but we don't have to here. Now we're simply going to use our definition of logs. Again, log base b of a is equal to x can be converted to the exponential equation. B to the x is equal to a. B to the x is equal to a. So once we get our log by itself, we're going to undo the function by simply using that definition. So this log equation becomes 7 squared equals 4x plus 1. Just use the definition to rewrite it. And now this is an equation in one variable, no problem. 7 squared is 49 equals 4x plus 1. Subtracting 1 from both sides gives 48 equals 4x, and then dividing by the coefficient 4 yields x is 12. Now we should take this value of x being 12 and substitute it in and see that it works, but it will. X is 12. All right, next. Okay. Solve the equations, check for extraneous solutions. Remember, particularly when we have some of these special equations, we can get solutions that don't work, so we need to substitute them back in to make sure. So we have log base 4 of x is equal to, plus log base 4 of x minus 12 is equal to 3. So step 1, get isolate our log. Well, notice here we have two logs on this left-hand side. So we're going to use our log rules to write this addition as a product. Remember rule 1. Ow. Shh. The product rule. If we have the log of a product, we can break it up into the sum. So if we have a sum, we can write the sum of two logs as log of one product. That's what we're going to do. We're going to use the product rule from the right side to the left side here. Forgive my dog. He's very angry about the mailman. The mailman is his arch enemy. All right, so we have an addition. We're going to write the sum of two logs as the product of one. Log base 4 of parentheses. I'm going to multiply x times x minus 12. So multiplying x times x minus 12, writing as one log, is equal to 3. All right, now we can employ our definition of logarithm to rewrite this. 4 to the third will equal this quantity in parentheses. 4 to the power of 3 is equal to x times x minus 12. Well, we're going to have a quadratic here. Distributing on the right-hand side yields x squared minus 12x. 4 cubed is 4 times 4 times 4. 4 times 4 is 16, times 4 more is 64. We have a quadratic, so we should set our quadratic equal to 0. I'm going to subtract 64 on both sides. So I get 0 is equal to x squared minus 12x minus 64. We can think quadratic formula. Maybe this thing will factor. And I think it's going to be factorable. So I'm going to try to factor this trinomial. Big X method. We know x squared is going to be x times x. We know there's a subtraction here, so one's going to be a plus and one's going to be a minus. 64, it could be 64 times 1. 16 times 4 could be 8 times 8. I think there's some more, but it's going to be this, 16 times 4. When our bottom, our AC here is a negative, we know that the signs are going to be different. One's plus, one's a minus. So we're looking for our pair of factors that sum for that negative 12. In this case, it'll be negative 16 and a positive 4. Keeping in mind, when we're summing and the signs are different, it behaves like subtraction. 16 minus 4 is 12. Whichever one there are more of gets the sign. There's more negatives, so the sum will be negative. So we're going to have 4 plus 4 and minus 16. All right, this is equal to 0. So our zero product property says if two factors are multiplied together to be 0, one of them must be 0. We could say x plus 4 is 0, or x minus 16 equals 0. Adding 16 to both sides here gives us x is 16. Subtracting 4 gives us x is negative 4. Minus 4, adding 16. So we think these are our solutions. One of them might not be. We got to go back into our original with negative 4 and 16. Well, negative 4 is going to be extraneous. If I attempt to take log base 4 of negative 4, so I'm looking at just this portion right here. Log base 4 of negative 4. Well, that's undefined. Think, 4 to what power is negative 4? There is no such power. The log functions are undefined for any 0 or negative. We can't even get 0 here. 4 to no power will yield 0. So if you end up trying to evaluate the log of a negative, that's going to be extraneous. Negative 4 is extraneous. Positive 16 will work. And you can put in positive 16, but you would see that I'm going to go ahead and do it. Let's look at 16. Log base 4 of x, where x is 16, plus log base 4 of 16 minus 12 is 4. Is that equal to 3? Well, 4 to what power is 16? 4 squared is. You could use your calculator if you have doubts. This is 2. Remember, when the base and what we're evaluating is the same, this is 1. That makes sense because 4 to the first is 4. And 2 plus 1 is indeed 3. That's a true statement. So our only solution, x equals 16, is the solution. I will write a solution. X equal negative 4, this one's extraneous. It worked in the modified equation, but not in the original one, and that will often happen with our special equations. All right. Very similar problem as our previous one. Log of 2x plus log of x minus 5. First thing to note, when it doesn't give us the base, it is the common logarithm, which is log base 10. I don't have to write that, but I will. If it just says log, it's an implied base 10. We call that the common log. If you have a slightly older calculator and it just says log on it, that's what the log is. So again, I'll use my product rule to write this as 1. So I have log of 2x times x minus 5 is equal to 2. Now we will use our definition of a logarithm. And we have log base 10. This base to this power is equal to this quantity in parentheses here. So 10 squared is equal to 2x times x minus 5. I'm going to leave this one for you to do. We could distribute over here. We got another quadratic. You're gonna you can use the quadratic formula, or you can factor. It's a quadratic, so set equal to 0. Then consider factoring like the previous one, or quadratic formula always works. Factor or quadratic formula. I will leave that one for you to do. All right. Number 13. Number 13 is going to be quite a bit easier, and I'll show you how we can handle this. Here we have log base 5 of 2x plus 7 is equal to log base 5 of 4x minus 1. Our log function is a one-to-one function. What I mean by that is if you graph our log function, remember our exponential looks something like this, and our log function gets asymptotic here. Our log function is asymptotic here, and it increases. That's a terrible drawing, but they would be symmetric about the line y equals x. This function here is 1. This function here is 1-to-1. What I mean by that is not only is it a function from x to y, but it's a function from y to x. Every x goes to a unique y, every y goes to a unique x. It would pass not only our vertical line test, if we drew vertical lines down it, but it would also pass a horizontal line test. Since that is the case, if you have log of something equals log that same base of something else, the insides must be equal. Here's the rule. Log base b of some quantity x, if that's equal to log base b of some quantity y, it must be the case that x is equal to y. This makes total sense. You're not going to have log base b of 10 equal log base b of 7. The x and the y, if these two quantities are equal, the x and the y must be equal. So if we have our equation and we have isolated the logs on both sides and there's no other quantities outside, added or subtracted or multiplied or divided, we can simply let those two inside parentheses be equal to each other. I think this makes sense. If this line is true, it must be true that the inside stuff has to be the same. Log base 5 of something equals log base 5 of something else. The something and the something else must indeed be the same. That probably makes perfect sense to y'all. So solving for x here, we'll subtract 2x on both sides. This leaves 7 on the left and 2x minus 1 on the right. Adding 1. 8 is equal to 2x. Dividing by 4x is 4. And we'll show substituting this in. Substituting 4 here, so 2 times 4 plus 7, that's 8, that's 15. So what we have on the left-hand side is log base 5 of 15 equals, on the right-hand side, substituting 4 times 4 is 16 minus 1, well, that's 15 too. This is equal log base 5 of 15. So clearly, log base 5 of 15 will equal log base 5 of 15. That's a true statement. So x equal 4, this is a solution. And that concludes this video.